welcome now Jordan Belmore and Stephen Payette, and you guys can take it away. Thank you very much and enjoy.
Thank you, Jordan. Thank you, Kizem. Thanks for the intro. Hello, everyone. My name is Jordan Belmore. I'm here with my colleague, Stephen Payette. It's great to see. I recognize a lot of names in this Zoom meeting. This is pretty funny. I see some colleagues from MDA as well, so it's a pretty cool thing that we got everyone here across Canada. Stephen and I both work at MDA, as you can see, and today we'll go over a few things related to composites in space. So quick breakdown of our presentation. Stephen and I are going to kind of introduce ourselves a bit more, give a bit of a background on our academic life and what who we are as people. We'll talk about MDA. We'll kind of give you a brief overview of what MDA does as a company, and then we'll start funneling down and going into what we do at the building where we work at, and then what composites are for MDA and where do composites fit when it comes to MDA. We'll go and briefly talk about our day-to-day activities, show you what we do as engineers at MDA within the composites group. We'll then jump to some recent programs or composite projects that we've worked on and kind of just show you a bit some of the difficulties or the challenges that we've had to face as engineers. Near the end, we'll go over a case study. This is going to be interesting, I think, for a lot of people. We're going to show a recent example of something that we've had to go through. And we'll be asking the crowd, how would you go forward with the challenges that we're facing right now, and see how the crowd reacts. And we'll have some final thoughts to share with the group today. So a bit of background on myself. I'm from Montreal. I went to Concordia University and I did a bachelor's of mechanical engineering. During my 4 years in my bachelor's degree, I was part of the student chapter SE Baja. For those who don't know what SE is, it stands for Society of Automotive Engineers. I was part of the Baja group, which is an off-road type of vehicle. We do competitions across North America, mostly in the United States. That's where I first got my taste, first taste of composites. We laid up using some pre-preg, some carbon panels, basically very simple stuff. But that's where I first tasted a bit of what composites are. It was a lot of fun. Professionally, I started as an intern in 2014 at MDA, and I've been here since, basically. When I graduated in 2015, I started in the composites group, and I've been here since. So it's been 6 years full time. I've been in the composite groups since 2014 and I haven't changed yet. I'm someone who loves to cook. I love cooking quite a bit and I love to box when I have time. Obviously the pandemic has made that quite difficult, but that's how I like to keep in shape. And I have a very cute cat called Pompon. He greets me like this every day when I get back home.
Okay, Jordan, I actually don't know that I see the request control option, so you might need to click through for me.
Yep.
So, hi, I'm Stephen Payette, also from Montreal. Education background, I did both my bachelor's and my master's in mechanical engineering at McGill. My master's was studying out of autoclave composites under Dr. Pascal Hubert. Since finishing at McGill, I've been at MDA for 6 years as well. I started off in the mechanical design group and spent 2 years there before switching into the composites department with Jordan, where I've been for the past 4 years. A couple things about me. I love both hockey and F1. And I don't have a cute cat, but I have a very cute daughter who's crying in the room behind me and an 8-month-old puppy. So I don't get quite as much sleep as I'd like, but they definitely keep me on my toes. Next, Jordan. Perfect. So wanted to give you guys a little overview about who MDA is. If you're here, you saw the LinkedIn notification and so on, so you have an idea that MDA is a space company. We have a more than 50-year story of firsts, both on and above the Earth. Currently, we're over 2,000 employees, and we're growing quite rapidly at the moment. MDA has three main lines of business. The first is the Space Robotics Division in Brampton, Ontario. Then there is Geointelligence in Richmond, BC. And then there's where Jordan and I work, the Satellite Systems Division in St. Anne de Bellevue, which is just west of Montreal. Since I assume we have people from all over the country and perhaps international students as well, it's worth mentioning we have smaller sites in Ottawa, Dartmouth, and Canada, as well as in the UK and in the US. So the next thing we wanted to do was show a little video that it was released recently in line with the rebranding, and it should give you an idea of who MDA is and where we're going in 2021 and beyond.
I'll start the video now. Stephen, let me know if everything is okay.
Yep, all good. Jordan, it might just be me. I'm not hearing audio. So as I mentioned, that was just a little bit about MDA as a whole. It's a publicity video, nothing too technical there. Oh, I'm seeing your Outlook, Jordan. There we go. Next, we wanted to sort of dive deeper into where Jordan and I work and eventually how composites lead into this. So as we mentioned, we work in St. Anne de Bellevue, which is the Satellite Systems Division. We're a global leader in design, fabrication, and testing of innovative products for a bunch of different markets. In Montreal, we have sort of three main product lines: electronics, microelectronics, payloads, and antennas. Antennas are where Jordan and I work, and it's where you'll start to see some composite structures. Next slide. So within the antenna division, we basically produce products like what you see in the photos here. When we speak about an antenna, you might think of the antenna on your car for your radio, or a satellite dish for TV before everything went to fiber optic for the most part. And in essence, an antenna is a device that converts radio frequency, so microwave energy typically, between transmission lines in free space. So what we mean here are satellites with an antenna that's designed to send information back and forth from ground stations on the Earth to the satellite orbiting above. That information can be used for Earth observation, GPS, television, internet connectivity, government spying on each other, you name it. The basic components of an antenna are two parts. There's a feed, which we'll show in more detail on the next slide. but it's basically the device that converts RF energy and sends and receives the signal. And then there are curved reflectors that amplify and shape that energy based on the mission. So you go to next slide, Jordan. And where do composites start to fit in? Composites typically are used in two parts of a typical antenna for us, either a structural component or a performance component. When we talk about structural components, we're typically talking tower structures or panels, and their purpose is purely to hold performance parts in place. We'll get into some of the challenges of the space environment later and describe why this is a challenge, but the mission of these structural parts is to survive the aggressive launch environment, and then when on orbit, it's to hold performance parts in the position that we need them to be in. The performance parts, we're typically talking about reflectors, which are shaped surfaces that amplify or concentrate or disperse the energy that we're selling to our clients. And where this sort of comes into play is if you can imagine we're making a product whose end customer is Indonesia, for example. It's a country that has islands all over and large masses of water. And if you're selling a product that's meant to provide internet connectivity to people's homes, you're going to focus the energy over densely populated cities while dispersing it away from water or unpopulated areas. So these large composite reflectors that we make have complicated shaped surfaces done to passively shape that energy based on the mission that we're doing for our customer. And as you know, nothing stays the same shape over temperature. So we need to design these things to be as stable as possible across a wide range of temperatures. So next we'll zoom in on a typical antenna, if you do the perfect, Jordan. So this is what we would call a top floor antenna module. So this would sit on the top of a large satellite bus. They could be as large as almost a school bus. The antenna itself more in the 2 meters tall range. And what's called out on this slide are the feeds that I mentioned, the reflectors that I mentioned, and that central structure, which would be the tower or the structural component. Those towers are typically made out of composite materials, honeycomb sandwich panels, or a couple other technologies that we have. And the reflectors as well are honeycomb composite construction. So what this antenna does in essence is it transmits energy back and forth via an RF signal. So the payload, the satellite bus would be below this antenna. The electronics would send the signal up to the feeds, and the feeds are both sort of the mouth and the ears of transmission. So it will be the output, the transmit that sends the signal off of the reflector to Earth, as well as the input or the receive. When signals are sent back to the satellite from the ground station, it'll bounce off the reflector to the feed to be processed by the onboard electronics of the satellite.
So Stephen's kind of shown you a bit where we're using composites, but why do we really use composites for space? So there are a few challenges that we have to deal with when it comes to space structures. I've listed a few here, and we'll talk about a few of them and why they're important. There are two main challenges, or two events, if you want, that provide certain sets of challenges. There's the launch itself, and basically the environment while it's in orbit in space. So launching stuff into space is very expensive. You've probably heard of SpaceX and a lot of this whole portfolio now of new people who are on the market and sending stuff into space. So they're bringing down the cost to bringing stuff into space, but it's still very expensive. So mass is a critical feature that we have to deal with, because real estate is very expensive within the rocket, and B, because it's so limited in terms of space, and you want to put as much fuel as you can in a satellite so that it can survive and do what it needs to do in orbit. Every gram that you put in space is worth something. So mass is very important. The launch environment too, you've probably seen rockets launch and how aggressive and really intense those few minutes are, but the accelerations, the vibrations, the shocks and just the noise generated during those minutes are very, very intense. So we have to build things that are stiff, that are very strong, and we have to test all of these things at our facilities mainly to show that they can survive these environments. Once it's in space, we have a new set of challenges that arise. We have temperature ranges that can really drastically swing from roughly negative 175 degrees Celsius to plus 175. We're dealing with stuff in vacuum, and we have obviously radiation. You can imagine being closer to the sun and whatnot. There's radiation that starts playing an important role. Another important part that it's maybe easy to forget, but satellites don't necessarily have a repairman handy that we can just ship over up into orbit and repair stuff when it breaks. So reliability is something we have to deal with. We have to make sure that whatever we're sending into space is as perfect as it gets. We can't send stuff and hope that we can repair it down the line. So we have a design obstacle that follows. We're not selling millions of cars. We're not selling millions of golf clubs. We're basically selling custom antennas and custom products. And that means we have a very low volume typically. So when we have a very low volume, we can't necessarily invest in the most optimized approach for each design. What we do is we have customers that have unique needs, and we approach these needs with generic tools. So we have what is called our toolbox, or composite toolbox, and we invest heavily in robust and flexible technologies. So an example of this is on the bottom left, we have a composite antenna tower. It's basically a complex looking product, but at the base, it's made of flat panels that are machined, that are cut, that are bonded using a variety of products that we have qualified. And we do complex assemblies so that we can come up with different needs for different customers. On the right, we have strut towers, which are another approach that kind of uses the same type of Lego brick type of mentality. We invest heavily in, for example, struts, composite struts. So, tension compression members, and we have metallics that interface all of these struts. And basically, we're able to design a very complex tower, but using a Lego brick approach where we've really tested the heck out of these tubes. We know how they behave, and then we can design with this toolbox at hand. So we're basically making very complex and unique designs, but using generic products at a base. From a materials point of view, we're using a lot of carbon fiber, maybe Kevlar, fiberglass. We have a similar approach to materials when it comes to design. So because we have a very low volume, but we have very specialized needs, we end up using very specialized materials. And that means expensive materials. Because of the low volume, because we're using such specialized materials, sometimes we're put in a situation where sometimes it's just better to choose a material that is the best compromise between two things or two jobs, but it's not necessarily the best for each job. And that's something that we have to deal with constantly. It's a constant struggle, but it ends up being, for example, this is a classic example here that we're showing with some fabric types, fabric weaves. You can imagine maybe in a certain situation, a tape is probably, using a tape pre-preg might be the most optimized solution compared to a plain weave fabric. But instead we'll invest in the plain weave, which is maybe more flexible for our needs and more appropriate for our needs overall, even though it's maybe not the most optimized. Another thing that's very important when it comes to the materials is the cost of qualifying new materials is extremely high. We spend a lot of time and money making sure we understand the material when it comes to its CTE, how it behaves under temperature, how it behaves under radiation exposure, how it behaves under vacuum. Basically everything that I was showing before when it comes to the launch and in-orbit environment. So it's very expensive to change any little parameter. So we try to make something that's more robust for multiple jobs instead of very specialized for one type of job. The last point is we deal with a lot of customers that are hesitant to change. And the reason is this business has a lot of risk. You can imagine sending stuff into space and without the ability to repair. Some people rely on these satellites for critical applications, whether it be, your cell phone. Losing your cell phone for 6 months at a time is not really on the table. And so customers are hesitant to accept changes because they see that as risks. So it's also tough to always choose the next best material, knowing that customers might not really accept that change just to get that extra 2% extra stiffness, for example. So we've dealt with designs, we've talked about some of the materials, we've talked about what we do at MDA. So how do we actually build stuff? And we've decided quite a long time ago that the best approach for MDA is to have a kind of a hybrid approach. So a lot of the piece parts that we get done are outsourced. So our main partner is Stelia. We've been working with them for quite some time. They're absolutely amazing to work with. And that's actually how we met Kazem. Kazem worked at Stelia before, and this is how Stephen and I know him. There are other few people here on the call today from Stelia, so I'm sure you guys appreciate this slide. So we've decided to outsource a lot of our piece parts. So you can imagine the reflector shell itself is a piece part. We own the materials, we own the processes, but at the end, the touch labor, the curing equipment, the expertise when it comes to storing all the materials and whatnot, that resides with Stelia. And you can imagine one of the reasons why this is the best approach is, for example, an autoclave. An autoclave is extremely prohibitive in terms of cost for us to own one, whereas it makes more sense for a partner like Stelia to own one when they have multiple customers apart from MDA to work with. And so Stelia provides us with most of our piece parts when it comes to composites, and then we do the assemblies in-house. So those complex structures that we were showing, Stephen and I, those get assembled using the Lego pieces, let's say, that Stelia is providing to us. So all of our products are custom. So that means we don't really have specific production cells when it does get to MDA, when we do the assembly internally. So it means we have very flexible workspaces. We're kind of showing a rough top level, very old view of our assembly lab. At the end of the day, this is always constantly changing because our needs are constantly changing and the programs are constantly changing. And we have to be able to have a modular approach to how we deal with things. So sadly with COVID, we can't show you in person the lab. So instead what we'll do is we'll show you a video that kind of shows you a bit what's happening inside this lab. It's a few years out of date, but I think it sums up pretty nicely what we've done in the past few slides. And hopefully you kind of get a better feel for what we do at MDA. Give me 1 second.
The introduction of composites at MDA Montreal goes back to more than 25 years with the emergence of the first single-hulled structures.
Les matériaux composites sont devenus populaires dans les années 80. La première structure monocoque en composite est apparue chez MDA au début des années 90 avec MSAT.
Au début des années 2000, nous avons décidé de créer un laboratoire d'assemblage des composites à l'interne. Le but étant de diminuer nos coûts et de mieux contrôler les délais de production.
Une démarche audacieuse qui allait à contre-courant de la tendance industrielle mondiale qui prônait l'impartition et la sous-traitance. Un pari qui deviendra payant.
Over the years, the Composite Laboratory has expanded to reach a surface area of 10,000 square feet.
En 2008, nous avons mis en place un programme de qualification pour offrir une solution complète à nos clients comprenant les structures ainsi que les réflecteurs. Depuis ce temps-là, nos commandes n'ont fait qu'augmenter de façon exponentielle.
Le laboratoire des composites demeure constamment à l'avant-garde de nos processus. Des procédés innovateurs y ont souvent été mis à l'épreuve et étendus à nos autres aires de production. Avoir ce lab ici sur place nous permet d'avoir un contrôle maximal sur nos coûts, nos échéanciers et surtout la qualité de nos produits. Les gens y travaillant sont fiers et impliqués.
Bienvenue au composite. Aujourd'hui, on va faire le collage du sous-ensemble sur le réflecteur. C'est un des plus gros collages qu'on fait. On va prendre 5 à 6 personnes pendant 1 heure pour effectuer le collage.
En tant que technologue, nous travaillons à créer des méthodes d'assemblage conjointement avec les designers, les monteurs mécaniques ainsi que les différents départements. C'est un vrai travail d'équipe.
Innovation is essential in the laboratory. Many R&D projects are created there.
L'idée de membrure en composite assemblée chez MDA a été développée à partir de 2006 sous la forme d'un projet de R&D interne impliquant l'ingénierie et le département des composites. L'objectif de ce projet était d'avoir une configuration d'antenne alternative à moindre coût, tout en garantissant une grande stabilité thermique et une performance structurelle adéquate. Par la suite, quelques projets ont utilisé cette idée de façon de plus en plus complexe afin d'atteindre l'objectif d'avoir une tour faite exclusivement de membrures en composite.
Nos installations de composites sont supportées par une chaîne d'approvisionnement en grande partie locale. Notre travail avec nos fournisseurs locaux nous permet d'offrir le meilleur produit dans les meilleurs délais et au meilleur prix, battant dans bien des cas les services internes de nos clients. Afin de s'assurer que les structures en composite fabriquées par MDA soient toujours à l'avant-garde, nous menons de front plusieurs projets de R&D. Le plus récent projet de R&D, supporté par le programme STDP, Space Technology Development Program de l'Agence spatiale canadienne, est le réflecteur Mark II. Il s'agit d'un nouveau réflecteur à faible coût, très rapide à analyser et à construire. Son architecture simple permet de l'adapter à des antennes de toute taille. Notre première livraison de réflecteur Mark II se fera en mars 2017.
An effective composite structure results from skillful fabrication by dedicated assemblers. Close cooperation among design engineers, structural and thermal analysts, and manufacturing specialists ensures MDA products continuously evolve to benefit from emerging technologies while respecting hard-worn lessons from our long heritage. A successful design sets itself apart by its clean concept and low feature count. Exceeding customer expectations, delivering technical requirements on schedule and within budget distinguish MDA in the marketplace. The laboratory has enjoyed constant growth over the years and loyal customers, which points to a very bright future.
you guys enjoyed that video.
I hope everyone spotted a young Jordan at one point in that video. Jordan from 5-6 years ago. So the next part of our presentation is sort of to meet the objective of give you guys an idea of what the day-to-day of a young engineer at MDA in composites looks like. And as we've touched on, because everything is custom one-off designs, we really don't have a very typical day. Jordan and I are both what we describe as horizontally oriented. So we see every product that comes through the building that has composites involved in the product, which means we work with many different programs, many different managers, clients, and unfortunately means we're in probably too many meetings. One of the nice things about this is we're involved from start to finish. And what I mean in that is in the video there, it mentioned the Mark II reflector as an example. That was a development product that Jordan was involved in when it came through. And now we're involved in production of all of those as they come through. So we'll be involved in both R&D for product and process development. We'll be involved in working with suppliers, developing the specifications to which we're going to buy the materials we need. We're often responsible for coming up with the qualification plans, the mechanical testing required to know the allowables of the materials we're going to work with. And then once there is a product, it's gone through a program design and arrives at MDA for manufacturing. We're responsible for scheduling, staffing, or I should say having inputs on scheduling, staffing, layout and floor use, and costing to some extent. And then you get into what really drives both Jordan and I, which is when things go wrong. Because it's a low volume industry, there's no idea like, well, there's a problem with this one, we'll put it on the side and use the next one off the line. It doesn't work that way. We're only making one. So when something goes wrong, we have to find a way to fix it and work with that one. So that will be that will lead to typically what we call MRBs, material review boards, and root cause analyses. The end of the loop is we're also involved in implementing the lessons learned from any programs that go through or any large problems that we have to hopefully make sure they don't happen again in the future. So that would be the continuous improvement that we're involved in. So here we wanted to talk about a few interesting projects and challenges that we've had in relatively recent history. So the first one I wanted to talk about was for a Saudi Arabian company. And as you may be starting to imagine by now, most projects that we work on are in one way or another, there's something new. This just so happens to have been the largest, what we call thick panel that we had produced up to that time. And it's still actually the largest we've built to date. This is a product that Jordan was heavily involved in the development of early on. Now, because we're making one of each product, we have to rely on destructively tested coupons produced in parallel with the flight builds to make sure that what we're making meets our expectations. There's no lot testing. It's all, we're making one, so we'll produce these coupons in the same cure at the same time under the same conditions to validate our flight part. And in the case of this project, for the thick panel, those work in process coupons gave us some poor results. Our flatwise tensile coupons, which is a typical test, failed in the normal way, but at values about 65% of our requirement. And then 4-point bending coupons that we performed as well, I believe met the structural requirements, but were giving us a failure mode that wasn't what we're used to seeing. Next slide. So these failed work in process coupons led to more than 6 months of intense investigation with our client, with our suppliers, and with our internal team. There were multiple test panels done, and basically every aspect of the design and production was investigated. So we used typically a fishbone diagram to help structure these type of investigations. So a fishbone diagram basically takes the main aspects related to your problem and divides it up. So you'll investigate, is there something in the way I'm measuring a property that's wrong? Is there something wrong with the material itself? Am I working with it in the wrong way? Did I deviate from my method or my process? Was there something wrong in the lab at the time? Was the humidity off? So environmental aspects. Did somebody just make a mistake? Was there a technician on the floor who did something in the wrong way? Or if there's, machine involved, it could be, did the autoclave misfunction in some way? So that's a typical structure that we'll use to try and address these big problems to make sure that we're not overlooking something. Next slide, Jordan. So the lesson that's interesting in this one and kind of drives me insane is we never found the root cause. We were never able to definitively pin down exactly what went wrong. In the end, what we were able to find out is, for whatever reason, we couldn't produce a size of that part at that facility on that table in that autoclave. There were different combinations of things that did work, but we weren't able to figure out why the full scale part didn't. And in the end, rather than finding a root cause, we found a way forward. And the way forward was to produce smaller parts at another facility that were then joined together to create the final thick panel design. And the reason I like this example is it shows that in industry, finding a way forward is sometimes more important than understanding what went wrong. It's a bit unfortunate because it leaves you exposed to getting hit by the same problem again in the future. But your program and your client, in our case, because the volume is one, only care about you solving the problem for that one build. So the picture you see here is the final integrated antenna. So there's that large structure that's all attached to that base panel, which you can see sort of behind those four reflectors. Next slide, Jordan. And here, this is another program near and dear to me. This is one where I was heavily involved in the development of the Strut Tower product. And this project for a Brazilian customer was our largest and most complicated strut tower to date. So as Jordan mentioned before, that's a tower formed entirely out of single force members joined by metallic parts. So there's these composite tubes that link metallic points from one section to the next. This program also featured our largest our only 3-shell Mark II that we've built to date. I know in the video they talked about the Mark II as a recent product we've developed, so that's something new to us in the last 4 or 5 years. This was the only instance in which we built one that had 3 shells integrated onto one reflector. So these were both extremely complicated products from our point of view. And the interesting thing here is the problems we ran into, you'll see in the next slide, were in some ways extremely basic and had nothing to do with the complexity of the products or with the composites processes involved. So the first problem that got us, as silly as it's going to sound, had to do with threaded parts that didn't mate properly. It's important to remember that most composites products somewhere along the line will interface with metallics as well, and that there is a whole slew of problems that can show up on the metallic side as well. In this case, it turned out that we couldn't seat 2 metallic parts together because of poor tolerancing on the drawing and a lack of communication with the supplier about which dimensions were actually critical to us. Unfortunately, these weren't off-the-shelf bolts that you could just replace. These were part of unique, complex metal parts that had a 12-week lead time and are in the realm of $8,000 to $10,000 each. So there wasn't a simple grab another one out of the bucket and keep going. And we couldn't move forward with the build knowing that there was this gapping and that the structural model couldn't tolerate improperly seated metallic components. And the second problem that we ran into on this project, as silly as it's going to sound, was a technician who this can happen to anyone, had a screw that he was trying to put into a part, and it was cross-threaded and jammed. So he had a bolt jammed in another metallic component bonded to our composite panel. And in trying to free the bolt, decided to go grab a can of effectively WD-40 lubricant, sprayed it into the part to try and loosen the threads, which in the end got the bolt out, but led us to a large, painful investigation with a very picky customer about what are the impacts of that lubricant on the inside of our panel structure. As Jordan mentioned, because we operate in the vacuum of space, our core, our honeycomb core, is actually vented from one cell to the next. You need to be able to extract air from the core so that you don't pop your skins when you go from pressure of ground to vacuum of space. And that meant that this large volume of WD-40 he sprayed in there we had no idea the impact and how far it had spread within the panel itself. What were the impacts on the core? What were the impacts on the film adhesive? What were the impacts on the composite skins themselves? So what I like about this program, again, is it shows that you can have the most complicated composites product out there, and you cannot neglect some basic things like your metallic components and the way your guys put them together. You have to make sure that you know what tools you're giving them and they have the right methods and the right tools to get the job done. And you really can't neglect things that you might think are quite simple or basic. So I think at this point, that was sort of the end of the presentation part. I believe Kazem wanted to run his poll before we get into our case study.
Thank you, Stephen. So I'm just going to run the poll. Again, there are just 3 questions, very simple. If you rank the presentation, it will be great. At the end of this year, we're going to have an award night, and we'll have a $1,000 award that will be given to the winner of the presentation. So I'm just launching that right now. Thank you. So again, just 3 simple questions ranking from 1, the least, to 5, the highest. Okay, you're at 80%. I'm just going to give it another 20 seconds. 92%, thank you. Okay, 10 seconds and I'll end the poll. Perfect, thank you. Go ahead.
Thanks, Kazem. So I think today this is going to be pretty interesting. We're going to kind of shoot a little case study, a very simplified case study. I'm going to introduce the problem. I'm going to give you guys a bit of some observations, some quick facts. For the sake of time, we've really reduced the number of facts, and the intent is at the end of this introduction, I want you guys to reflect on how you would approach this problem concretely. So we work with Stelia, and this is a problem that's happened over the past year. This is a laminate that was built using a Kevlar fiber and a cyanide ester resin. It's using a process that's cured in an autoclave under vacuum. After the cure cycle was done and the technicians demolded the laminate, they noticed that there were blisters on this laminate. We used a high intensity light, and when we were able to look through this laminate, and we're able to see that there's something weird happening with this laminate, but only on one section of it. And so we take a look, and there's a few facts that come out of this. The cure cycle itself went well. Everything was per spec. The material that we bought was per spec. There was no anomalies at that level. The layup was done on a flat aluminum plate. That was normal. The blisters that are occurring on both the tool side and the bag side of this laminate. We perform mechanical coupons on sections of this laminate that were of a lower ply count. And they're good. They actually meet our requirements. They're exactly where we want them to be. This laminate has various ply counts. There's a 6-ply section, there's a 14-ply section, there's a 16-ply and a 24-ply. But the blisters only occur on the 24-ply section. Knowing this, what do you do next concretely? What do you do? How would you investigate this, and what is your next move? That's what we want to know.
Perfect. Thank you, Jordan. And again, I just want to mention that we are going to use the breakout room. Yes, it's a technical question, but we use it as a kind of a social gathering and discussions and networking for students, because we have a lot of professionals here in the 7 as well. So don't be discouraged when I launch the breakout room. So I'm going, and stay there. You can just say hello. Let's even leave it at that. And we don't really have that much time, so I was just going to give it 5 minutes. And then if you want to be really methodological about it, so perfect, have a quick discussions and come back and report to the group. So we are 40. Again, it's a social gathering. I'm just going to put you in different breakout rooms. So I'll do, let's say 8 rooms of 5. And so I just created the room. Thank you.